Hi everybody, it's Mr. Conboy. In this video, I would like to revisit the chemical energy graphs that we did in the fall of ICB 1 and use our knowledge of bonds to understand them better. Let's consider the chemical reaction that you have carried out so many times in the lab. CH4, which is natural gas or methane, plus two oxygen molecules is combusted and turns into a carbon dioxide molecule and two water molecules. By now, you may recall that this is an exothermic reaction. Exo because of the fact that energy is released from the reaction into the surrounding environment. So the exo refers to the outward flow of energy out of the reaction into that environment. Now, let's recall a little bit what we know about a graph that describes such a reaction. The graph plots the reaction's progress on the x-axis, the amount of potential energy at any one moment on the y-axis. We do know that all the stuff on the left side of the arrow represent the reactants, and all the stuff on the right side are the products. So at the beginning of the reaction, we can imagine the reactants at the far left, methane and two oxygen molecules. And then as they react, they turn into some products that are at lower level of potential energy. Now, we never explained why they end up being at a lower level of potential energy, but in this video we're going to do that. Now, let's think a little bit. We have said that the potential energy goes down during this exothermic reaction. Well, that means that according to the first law of thermodynamics, that energy can't be destroyed, but it can change forms. So all that potential energy that's lost must be converted into another general form of energy, which we've before called kinetic energy. And that's energy that's easy to observe. That would be the energy found in the flame, in the warmth, in the sound created during the combustion of methane. Another portion of the graph that we should probably pay some attention to is this part here, which we called activation energy. From here on out, I'm going to use a shortcut to describe it, E of A. That's a subscript A, energy of activation. You may recall that's the amount of energy needed to get the reaction going. If you have a Bunsen burner and you have methane flowing through it and you have oxygen in the room, that by itself is not enough to release heat and carbon dioxide and water. You have to first have some sort of kickstart energy to get things going. And that could be a lit match or a spark from your striker. Remember then that that is an example of activation energy. We're going to talk a little bit about all these concepts, but at greater depth using our new knowledge of bonds. What I'd like you to do is take a little bit of time and hit pause on this video, make the Lewis dot structures for every molecule shown in the balanced chemical reaction that we have here. And then once you're done making those Lewis dots, resume the video and let's see if they match the Lewis dot structures that I make. Okay, please check yours against mine. Hopefully it all works out. Here's methane. We have 4 bonds between carbon and hydrogens. Here we have 2 molecules of diatomic oxygen. Note there must be a double bond between the 2 oxygen atoms in each molecule. Our carbon dioxide consists of 2 double bonds from the carbon to each of the oxygens. And notice we have single bonds between the oxygens and hydrogens in water. Okay, let's move on talking about 2 basic facts about chemical reactions. When you have a chemical change, that basically means that the substances you start with, the reactants, change what they're bonded to. That means that bonds have to be broken and then new bonds have to be reformed. Well, it turns out that when bonds are broken or dissociated, energy from the environment is absorbed, meaning energy must be spent to break those things up. Just like breaking a window or breaking a piece of ice requires energy from some external force, from external direction. Now, to form new substances, that means you have to form new bonds, and that does the opposite with energy. It releases it into the environment. These two basic facts, combined with some knowledge about Lewis dots and some data about bonds, can carry us a long way in understanding why our chemical reaction here is an exothermic one. So let's take a closer look. If we look at our Lewis dots up here in the upper right-hand corner, we can see that methane, CH4, for it to be broken apart, it has to have 4 of its bonds dissociated. Well, we have this data table from page 236 of your book that's telling us that there are 4 carbon-hydrogen bonds, and each of those bonds requires 393 kilocalories per mole. I'm getting it right here on the table. Takes that much energy to break those bonds. So if you take 4 and you multiply it by 393, you're going to get the total amount of energy needed to break up a methane molecule. That is 1,572 kilojoules per mole. Now, the other molecules whose bonds would have to be broken for this reaction are the 2 oxygen molecules. Now notice that each of them have double bonds. You'll see that on this table there's no description of the amount of energy needed to break a double bond between 2 oxygen atoms. Now you might say that it makes sense to predict that the amount of energy needed to break a double bond of oxygen maybe would be 2 times the amount needed to break a single bond between oxygens, which is 142. So you might use your common sense and say, oh, well, it would take 284 kilojoules per mole to break a double bond. Well, actually, it turns out that's not true. Our observations are that lots of double bonds require more than twice as much energy to break than the amount needed to break single bonds. So I had to go to another website and find some other data to tell me how much it takes to break a double bond between oxygen. So it turns out that to break a double bond between 2 oxygen atoms, you need 497 kilojoules per mole. Now, keep in mind, though, if you look over here at our balanced equation that's now represented with Lewis dots, there are 2 of these double bonds we have to deal with, 1 for each oxygen molecule. So that basically means that I have to take 2 times 497. That's telling me that there are 994 kilojoules needed to break down each mole of the oxygen molecules involved. To break down all the moles of oxygen molecules involved. So the total amount of energy needed to break all the bonds to make this reaction possible is 1572 plus 994. So in other words, 2,566 kilojoules per mole. So now our next step is to think about how much energy would be released when we form the new bonds to make the carbon dioxide and the 2 water molecules. Well, we can actually use the same sort of data table. The amount of energy that is required to dissociate a bond is the same amount of energy that's released when one of these bonds is formed. So we can actually get double duty out of this data table. So let's think about the bonds that have to be formed. We have to be able to form a bond between carbon and oxygen that's a double bond. We have to be able to do that 2 times in order to make that 1 carbon dioxide molecule. And we can see from our data table that a carbon dioxide molecule, that a carbon to oxygen double bond is 736 kilojoules per mole. So 2 of them gives us, of course, 1,472 kilojoules per mole. That's the amount of energy that would be released upon the formation of our 1 carbon dioxide molecule. Now we have 2 water molecules. Each one of them involves hydrogen to oxygen bonds. Each molecule, though, involves 2 of those bonds, but we have 2 molecules of water, so that means a total of 4 hydrogen to oxygen bonds, and each one of those is 464 joules per mole. So the total amount of energy that would be released upon the formation of those water molecules is 1,856 kilojoules per mole. So the total amount of energy that's going to be released when we form these new bonds for all of our products is 1,472 plus 1,856, giving us a grand total of 3,328. Now at this point, I want to use that mathematically determined data to prove to you why the reaction is exothermic. You already know that it is. You see all the energy that's dumped at the end of the reaction. The question is, why does it end up that way instead of being endothermic? So what we need to do is let's start off and consider our reactants. We'll just choose a place kind of in the middle of the y-axis as the original potential energy that we have. Now, we know from the math that we just did that to break all the bonds with our reactants, we know that a total of 2,566 kilojoules per mole is required. So if it's required, it means it's energy that has to be put in to the system to make things go. Gosh, that sounds a lot like an uphill battle. It sounds a lot like activation energy. So what we can do is essentially think of this uphill struggle continuing until we get to this maximum point right here. And the amount of energy needed to make that uphill struggle is that 2,566 kilojoules that we calculated just a little bit ago. That is our energy of activation. So we're essentially saying that your striker or your lit match has to provide at least 2,566 kilojoules to break down a mole of methane and to light it on fire in the presence of oxygen. But we also showed mathematically that the formation of the new bonds in our carbon dioxide molecule and water molecules is going to release energy to the environment. So that sounds like a downhill process. Furthermore, we calculated that the amount of that release is greater than the amount that was absorbed. So I'm going to draw a longer arrow to represent that. And I'm going to sort of draw my downhill to be that equal length, like so. And the size of that release of energy we determined to be 3,328 kilojoules per mole. So now if we look at this hill, let's look at that maximum point of energy, draw a dotted line down from it and one across, like so. Essentially, we can say that this time here, circled in yellow, represents the time when bonds broke. And that the time represented by the other side of that point, actually, sorry, from that other side all the way down to this platform here, represents the time during which new bonds were formed. So in the end, we have the energy state of our products indicated by this platform here, and we know that these products now have 762 fewer kilojoules per mole than they had at the beginning. How did I get that? Basically took 2,566, subtracted it from 3,328. So 762 kilojoules per mole of energy, of potential energy, was lost over time to the environment. That's the light and the heat. So now I've proved why it's exothermic, and have shown that it was using our knowledge of bonds that helps us understand that. That's pretty cool.